Hi everyone, this is Dr. C. Manjunath, Associate Professor, Department of Chemistry, RV College of Engineering. Excuse me. In continuation to my previous recording about computational chemistry, which comes under chemistry of smart materials and devices, I have covered in my previous recording about the molecular modeling, the scope, the cost, and efficiency, computational modeling, interactions, etc. In my previous recording. In this second part of this unit, that is molecular topology, I'll be discussing in this recording covering about molecular topology, topological matrix representation, vertex adjacency, and edge adjacency and distance matrix in this second part of this unit. So let me go to that part. Okay, I have just discussed about bond various interactions, non-covalent and covalent interactions in my previous recording. I'll be just continuing with molecular topology. So once you understand that molecular interactions, both covalent and non-covalent interactions, how that the interactions are being represented in numerical form. So that we are going to discuss under molecular topology. Molecular topology deals with how atoms are connected in a molecule rather than how they are arranged in 3D space. It is just explaining how they are connected. Okay, it converts a molecular structures into a mathematical graphs to predict the molecular properties. So we know that the molecular properties actually depend on how the atoms are interacting and how the atoms are linked to each other and how the functional groups are interacting, right? These interactions arises actually due to how atoms are connected in a molecule. And we know that different connectivity leads to different interaction patterns. Computers cannot see these interactions directly. They first need a simplified structured representation. So therefore, we use the molecular topology to represent that interactions into some structural forms, mathematical forms. Molecular topology converts a molecular structure into a graph-based form. So atoms in this molecular topology, atoms are treated as vertices. Vertices are nodes, and the bonds are treated as edges or connections. So it captures the connectivity responsible for interactions. So overall, the interactions that we have discussed in my previous recording, the molecular interactions, covalent and covalent, and their connectivity. And in this recording, I'll be discussing about the connectivity and topology, the representations. So overall, this molecular topology converts from interactions to connectivity, connectivity to topology, topology to mathematical representation, so that the computer can understand that. So let us understand the network and graph in computational chemistry. Of course, you have studied graph theory in mathematics with respect to various other applications. But with respect to computational chemistry, let us understand the network and graph. So we know that the network is a collection of interconnected entities in general, right? A graph is a mathematical representation of a network. So a network is a collection of interconnected entities. A graph is a mathematical representation of network in general. In computational chemistry, we know that atoms are treated as vertices or nodes. The bonds or interactions are treated as edges. So in molecular graph, for example, with respect to the molecules, the materials, the molecular topology represents the connectivity of atoms in a molecule. Connectivity of atoms in a molecule. Of course, it knows 3D geometry. It means it represents only how they are connected, not how they are arranged in 3D space. It focuses only on bond connections. It simplifies the molecular structure for a computer analysis. You can see that this is aspirin 2D, in two-dimensional aspirin structure. It is represented in the form of graph like this, 2D topological graph. You can see that the carbon atoms are represented by one type of vertices, that is black circle that is represent the carbon vertex, and the oxygen, the CO, the double bond, and OH oxygen is represented by the blue color circle, right? And you can see that single bonds are represented by one color, a double bond, an aromatic bond, etc., etc. So this is how the chemical, a molecule, is represented in the form of graph. Similarly, aspirin 3D. So this is aspirin in 3D structure, three-dimensional. The 3D geometrical graph is represented like this. Okay, so it is with respect to how closely the atoms are arranged in dotted lines that represents in 3D space. For example, the molecular graphs in molecular topology, as we have discussed, the atoms, always remember the atoms are vertices or nodes and the bonds are the adjacent connections. So let me take one example, ethane. Okay, C2H6, right? C2H6 is this is the structure, right? CH3 and CH3. In molecular topology, all the hydrogen atoms are suppressed. Okay, so we don't consider the hydrogen atoms. That is the first thing. So if we are not considering hydrogen atoms for the representation of the graph, then you will not be able to consider the edge also, CH edges. So this is also not considered. CH edge is also not considered. So therefore, for the ethane, it's consisting of two carbon atoms, means it has only two vertices, and there is only one CC bond, so one edge. Okay, since we are ignoring all the CH bonds and hydrogen atoms, so for the ethane, it is having only two vertices and one edge. So it simply represents a linear graph. So it represents only a linear graph like this. So this is a graph of ethane. So this is C1 atom and this is C2 atom, you can see. Similarly for propane, it is having three carbon atoms. So it is having so three carbon atoms means three vertices, or it's also called three nodes. Then two CC single bonds. So it has two edges. So it forms this also forms a linear graph like this. You can say like this. This is the linear graph. It's a propane. For benzene is actually a structure. This is the benzene structure. This is C6H6. This is the molecular formula, right? This is the structural formula. C6H6 is the molecular formula, and this is the structural formula. In molecular topology, we do not consider hydrogen atoms. We suppress that. Okay, this is not being considered. It's ignored. Okay, since hydrogen is ignored, then there is no point in considering the CH as one of the H, right? So therefore, it is having one atom, 1, 2, 3, 4, 5, 6. Therefore, it is having 6 nodes or vertices, and 1, 2, 3, 4, 5, 6. So there are 6 edges. So therefore, it forms a cyclic ring like this. This is the graph for it. And we ignore double bond also. So double bond we represent in different descriptors. So molecular topology. So this is a simple cyclic graph. High symmetry and uniform connectivity. Similarly, cyclobutane has 4 vertices and 4 CC single bonds. So therefore, it is having 4 edges. It forms a square, graph. This is the graph. Okay, so this is the graph. Actually, in the structure, we write like this. This is the structure of that cyclobutane. This is the molecular structure, right? This is represented in the form of graph. This is actually the graph of cyclobutane. So we have simplified the structure. So once a molecule is stated as a graph, we can represent this graph by using matrices, so that that computer can understand. What is graph? In computational chemistry, a graph is a mathematical representation of a molecule. Okay, it's a mathematical representation of a molecule. Like in butane, the structure is being converted to square plane ring, right? Cyclic ring. So that is called graph. where atoms are vertices and chemical bonds are edges. So the mathematical representation for a graph is G is equal to graph is equal to the combination of vertices and edges. V represent the set of atoms, vertices, and E represents the edges, set of chemical bonds. So there are various types of graphs are used in computational chemistry. Simple graphs like single bonds, no loops like alkanes. Cyclic graphs like ring structures like benzene and cyclobutane. And weighted graphs. So edges carry bond order or a distance or some other heteroatoms. So there are various types of graphs. That depends on the molecule structure, the atoms. So in graph theory, in mathematics and in computers, you actually study various types of graphs. You can see this is in general, computer science engineers studying various graphs. Unidirected graph, and this is directed graph. You can see it is being directed, and space graph. It is open, and complete graph, dense graph. Cyclic graph, it is cyclic graph like this, and this is being cyclic graph. And acyclic graph, this is there is no loop here. And weighted graph, so these are being labeled E, B, and different this one. And unweighted graph. Okay, so these are the various types of graphs that you actually study, but in chemistry we don't discuss. In this unit we don't discuss this, only for general information. Okay, the basic notations in molecular topology are adjacency. Okay, this one. Adjacency means the two vertices, means the two atoms, U and V, are adjacent. If there is an edge, U comma V. In chemistry, two atoms are adjacent if they are directly bonded. So that is the meaning of adjacency in molecules in chemistry. Vertex degree. Degree of vertex, the number of adjacent vertices excluding hydrogen atoms. If the carbon atom is bonded two more carbon atoms, then its vertex degree is 2. Okay. In molecules, the number of bonds connected to an atom is called vertex degree. Path, a sequence of vertices, U1, U2, like that, UN. Each consecutive pair, UI and UI plus 1, the next neighboring atom is an edge. It represents the bond pathway between the atoms. Next, we have a circuit. So notations, a closed path where the starting and ending vertex are same. So that is called circuit. Indicates the presence of ring structure. Then we have a cycle, a circuit in which all vertices appear only once, except start and end. Okay. So example, carbon in a benzene ring is a cycle. Simple graph, a graph with no loops and no multiple edges. Okay, most molecular graphs are treated as simple graphs. Connected graph, every pair of vertices is connected by at least one path. So these are, it is, I mean, if it is connected by one more, that's called connected graph. Represents single or continuous molecule. Tree, a connected graph without cycles. Okay, this represents acyclic molecules like alkanes or branched one. Let us understand how these graphs are being converted to matrix. Okay, matrix representation is a mathematical way to describe that molecular graph. It converts a molecular connectivity into a numerical form because our computer can understand only the mathematical formulas and numericals. It is essential for computer-based analysis for molecules. Why matrix representation? Computers, cannot directly process the molecular drawings. So matrices provide a systematic and compact representation of any given molecule, right? So this matrix representation is used to calculate topological indices that I'll discuss in the upcoming slides, and the molecular descriptors in the next recording. So what are the various types of matrix representation that you're going to study? The first one is adjacency matrix. Adjacency matrix. It shows direct bonding between the atoms. So element 1, if atoms are bonded, or else 0. Okay. Distance matrix. This is second one, the second type of matrix representation. It shows the shortest bond distance between the two pairs. So the distance matrix will give you the distance, the shortest bond distance. So number of bonds are, how many number of bonds are being separated? Okay. So the number of bonds separating two atoms, this is called one element. Next, we have edge adjacency matrix. It represents the connectivity between the atoms. Edge adjacency is with respect to bonds. Okay, so useful for studying the branching and cycles. Overall, the matrix representation translates molecular graphs into numerical form for computational analysis. Okay, let me discuss the four matrix representation. The first one is vertex adjacency matrix. What is the meaning of this? Vertex adjacency matrix represents atom-atom connectivity. Vertex means what? Atoms. It's also called nodes in a molecular graph. So rows and columns correspond to only vertices. Okay, now they are connected. For a graph with n vertices, in this case of vertex adjacency matrix, so A means adjacency. Aij, the matrix representation, Aij is equal to, if Aij is equal to 1, it is labeled as 1 when if the vertices I and j are directly bonded. Okay, if they are directly bonded, I and j are two vertices, they are directly bonded, then for that, it is those two, the vertex, we define that as 1. If they are not directly bonded, okay, then it is 0. So in this case, the diagonal elements will be 0 because no self bonding. What is the significance of this vertex adjacency matrix? It captures the molecular connectivity used to calculate the vertex degree, and Zagreb indexes I will be discussing in the next video, and also the foundation for QSAR and QSPR. So this will be covering in the last the part of this unit, the fourth video of, okay, structure activity relationship and structure property relationship, QSR, quantitative structure activity relationship and quantitative structure property relationship. So these are the tools used to study the molecules. Let us look at the conditions for vertex adjacency matrix. For a graph with n vertices means number of atoms, number of nodes, right? The matrix is of order n cross n, n into n. Rows and columns represents the vertices. So if vertices I and j are directly bonded, it is represented 1, otherwise 0. Diagonal elements are 0 because their diagonal elements are always connected to the same element. Aii is equal to 0 or Ajj is equal to 0. So the matrix is symmetric, therefore Aij is equal to Aj. So both will be 1. So applicable to simple graphs, no loops, no multiple edges. These are the conditions for vertex adjacency matrix. Let us understand the representation of a molecule into a vertex adjacency matrix by taking ethane as an example. So C2H6 is the formula, and this is the structure. This is the chemical structure of ethane, and this is the graph. Okay, this is the graph for this. So this is C1 and this is C2. So this ethane has two vertices, C1 and C2. This is one vertex and this is another vertex. The edge is only C1. This has only one edge. This has two vertices and one edge. So therefore, the adjacency matrix for this A adjacency vertex adjacency matrix for this ethane C2H6 is 0. See C1. So this is AII. This is 1 and 2. 1 and 2. Okay. So here the vertex 1, C1 is not connected to C1. That is AII is equal to 0, right? That is a condition. and C1 is connected to C2. These two are adjacent to each other, so therefore it is 1. Then the second 2 is connected to 1, so it will be, so 2 is connected to 1, so therefore this is Aij is equal to 1, and the diagonal elements will be 0. Okay, so the conclusion for this is the simple matrix shows CC single bond. The degree of each carbon is 1 because they're connected to only one atom. Next, let us look at the propane C3H8. You can write like this: C1, C2, C3. So therefore, how many vertexes? There are 3 vertexes and 2 edges. So C1, C2, C1, C2, and C2, C3. So these are the edges. So therefore, adjacent matrix for this one is so C1, C1, 0. This is 1, 2, 3. You can say 1, 2, 3. C1, C1, AII is equal to 0. So 1 and 2 are connected. So C1 and C2 are adjacent. Therefore, it is defined as 1. And 1 and 3 are not connected. So these two are not adjacent. So therefore, it is labeled as 0. Next, coming to the second carbon. Second carbon is connected to the first carbon. Second carbon is connected to first carbon. Therefore, it is represented as 1. And so diagonal elements are 0 because 2 is not adjacent to 2. It's not it itself. Then 2 is second carbon is connected to third carbon. So it is represented as 1. So it is adjacent. Similarly, for the third carbon, third is not connected to 1, it is represented as 0. And third is next to 2, therefore it is represented to 1. So therefore, this is the matrix representation of propane, vertex adjacency matrix. So the conclusion is the middle carbon has higher degree. The middle carbon, second one. So you can see that it is having 2 ones. But in the first and second one, we have only 1 in the matrix. So this is what that computer can understand from this matrix. It understood that the central carbon will be having a higher degree. So this reflects the chain kind of structures. Next, let us understand for the steps involved. How do you construct a matrix for this? Okay. First, you should identify the vertex. If they give you the molecule like this, this is 2-methyl butane 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, so this is 2-methyl butane. If they mention 2-methyl butane, you have to write the molecular structure like this, and the molecular structure is converted to graph like this. Then you should number it. If they have not numbered, each vertex should be numbered like 1, 2, 3, 4. Then the first step is identify the vertices. So there are 5 vertices in this molecule. Then once you identify the vertices, identify the edges. Okay, so here C1, C2, 1 edge, 1, 2, 3, 4. So there are 4 vertices. Vertex 2 is connected to, you can see here, this is vertex 2 is connected to 1, 3, 5. So vertex 2 has 3 edges. Okay, and vertex 3 has 2 edges. So therefore the edges are 1, 2, the carbon 1, carbon 2, 2, 3, 2, 5, and 2, 3, 2, 5, and 3, 4. So these are the number of edges for this molecule. 1, 2, 3, 4. 1, 2, 3, 4. So there are 4 edges. So first identify the vertex, then identify the edges. Then initiate the 5 because there are 5 vertices. 1, 2, 3, 4, 5. So therefore initiate the 5 cross 5 0 matrix like this. So then you define fill the matrix. Once you define the 5 cross 5 matrix, fill the matrix using adjacency rules. What is adjacency rule? So Aij or Aji is equal to 1. Okay, edge for edge, the adjacent edges are defined as 1, right? So there are 4 edges. So these are the 4 different edges. For all of them 1. For others it will be 0. Okay. So therefore you can see that 1, 2, 3, 4, 5. This is the 5 vertices. 1, 2, 3, 4. So the 1 and 1 will be 0. 1 and 2, 1. 1 and 2 are adjacent. So therefore it is defined as 1. So 1 is not connected to any, not other than 2. It is not adjacent to any other atom. 3, 4, 5. Therefore they're all 0. Okay. Next, the second carbon. Second carbon is adjacent to 1. Second carbon is adjacent to 1, and for 2 it is 0, and it is adjacent to 3 also, therefore it is 1, and it is not adjacent to 4, therefore it is 0, and it is 2 is adjacent to 5, directly bonds, therefore 1. So then we have for 3 0 1 0 1 0, and for 4 you can see that it is adjacent to only 1. 5 it is adjacent to only 1. You can see at the third carbon it is having 2 edges, and the second carbon is having how many edges? 3 edges, 3 vertex, 3 it's bonded to 3. The degree is high. This is what that computer will understand from the matrix. So the vertex adjacent matrix converts the molecular connectivity, this molecular connectivity, into a numerical form, that is matrix representation, enabling computational analysis and calculations for topological indices. So this is another example for vertex adjacency matrix. You can see here, this is the representation 1 and 1. This is 1 and 1, 0. 1 and 2 are adjacent, and 1 and 3 is not adjacent, and 1 and 4 they are not adjacent, so therefore it is 0. Similarly, 1 0 1 1. This 2 is actually it is having 1. 2 is adjacent to 1, 4, and 3. So therefore it is having 1 1 1 in the matrix. Similarly, 3 is adjacent to second carbon and the fourth carbon. So therefore it is defined as 1. Others will be 0. And the fourth is adjacent to 2 and 3. 2 and 3. So you can see here this is the matrix representation of this molecule. You can just work out this. You can see here this is having 7 vertices: 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. So here from matrix represents that 1 is adjacent to only 2. For all the other, it is not adjacent. You can see 3 and 6. 3 and 6, 3 is 1 2 3. 3 is adjacent to 2 4 and 6. 3, if you go to 3, it is adjacent to 2, then 4 and 6. Okay, so more the ones in the matrix, more is the degree of that vertex. Similarly, this is 1,3-butadiene. This is the molecular structure, and this is the graph, and this is the vertex adjacency matrix representation. Similarly, you can work out for azulene. Azulene is having 10 vertices, therefore it is called 10 cross 10 matrix. You exclude that this is the molecular structure, and the graph would be this is the graph 1 2 3 4 5 6 7 8. This is 9 and 10. This is the graph. This is the graph for this, and this is the molecule azulene. So this is being converted to graph, and graph is being converted to matrix. You can see that 9 is adjacent to 1, 8, and 10. You can see that this is the 9. 9 is adjacent to 1, and then 8, and then 10. And similarly, you see 10. 10 is adjacent to 3. 10 is adjacent to 3, 4, and 9. 3, 4, and 9. Okay. So this molecule is converted to graph, and graph is represented to matrix representation. So that is about how the relation between the two atoms in a molecule, that is called vertex adjacency matrix. The second one is edge adjacency matrix, EAM. So this represents, the edge means what? The bond. How the bonds are related to each other, whether they are adjacent or not adjacent. So that information is represented by edge adjacency matrix. It represents the bond-bond connectivity. Two edges are adjacent if they share a common vertex. Example, edge adjacency matrix is Ij. If the two edges are share a common bond, common atom, common vertex, then it is defined as 1. Otherwise, it is 0. What is significance? Useful for analyzing the branching applied in a plot number. I'll be discussing in the next video calculations. Let us understand the edge adjacency matrix for propane. Okay, propane, the molecular formula is C3H6, that is CH3, CH2, C3H8. So it is having three C1, C2, C3. This is the 2, 3. Okay, this is the graph, a linear formula. It is having 3 atoms, 3 vertex, but it is having only 2 edges. So what are the 2 edges? C1, C2. This is one edge. This one, and C2, C3. It is having only 2 edges. So therefore, edge adjacency matrix is equal to, so edge 1, E1, E2. This is E1 and this is E2. So E1 is 0 because, and E1 and E2 are adjacent. Therefore, it is defined as 1. Similarly, E2 and E1 is 0 and E2 and E2 is 0. So this shows how the bonds are being connected. So it helps in quantifying the branching. Let us find the matrix for this graph. You can see that this is two different molecule. We get the same matrix, edge adjacency matrix. This is one of the limitation. So therefore, only edge adjacency matrix cannot give the clear, complete information about the molecule. Here A, B, C, there are 3 edges. Here also there are A, B, C, 3 edges. A, B, C. So this is one edge and this is another edge and this is another edge. A, B, C. For both of them, we get the same matrix. Okay. So this is a 2-methyl propane and cyclopropane. It's a graph type is, this is a branched one, tree-like, and this is cyclic. Number of edges are 3, 3. The edge adjacency matrix for both same 3x3 fully connected, 3x3 fully connected. So reason for adjacency is a central branching and is a ring closure. So the structural insight is it represents the branching and represents ring strain. So edge adjacency matrix cannot distinguish if a molecules like this. So this EAM, edge adjacency matrices, may look identical for branched and cyclic molecules, but the origin of connectivity is fundamentally different. Let us understand vertex and edge adjacency matrix comparison. So we have defined this is the one and also the second one, VAM and EAM. Let us compare for the particular molecule. Okay, so this is having 7 vertices. 1, 2, 3, 4, 5, 6, 7, 7. So this is the matrix representation for this. This is VAM, vertex adjacency matrix. You can see that the atom 3, the vertex 3, 1, 2, 3, 3. It is adjacent to second carbon and adjacent to fourth carbon, adjacent to sixth carbon. High degree. Even for 6 also. This is 6, adjacent to 3, adjacent to 5, adjacent to 7. But the edge adjacency matrix, this is EAM. For this, it is having 1, 2, 3, 4, 5, 6. This is also having 7 vertices. You can see that the matrix, edge adjacency matrix for this is not same. You can see this one. This row is completely different, and this row is completely different. Okay, and this row is not same as this one. You can compare these 2 rows. The first one might be same. The first one. Second one is same. This is same for both. Third one is different. These 3 are different. So this is how the matrix distinguishes the relation between the vertices and edges. Next, the third type of matrix is vertex adjacency matrix for weighted graphs. What is meant by weighted graph? A weighted graph assigns a weight to the edges. Weight may be, it may represent the bond order. It may be a single bond or double bond or triple bond. Or bond strength, it may be hydrogen bond strength is less. If it is a covalent bond strength is high. That is called weighted edges. Or interaction energy, or if there is any heteroatom, something like that. So weighted graph, W is equal to Ij, if the bond order and the weight between I and J, if there is a bond order is different, or if there is if they have given a weight to that vertex, the vertices which are adjacent, they're defined as vertices like I and J are different. For example, if one is carbon atom but other one is nitrogen atom, so then it should be made as Wij. So the significance is more realistic molecule representation. It's used for advanced quantitative structure activity relationship models. You can see this is one of the example for the vertex adjacency weighted matrix. This is with respect to vertex only. So how many vertices in this? You can see in this molecule there are 10 vertices, starting from 1, and this is 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this will get 10 cross 10 matrix. The definition for weighted adjacency matrix is if I and J are weighted with respect to bond order or with respect to different order, then that edge relationship, the relationship between I and J edges is defined as K. So you can see here, this is the heteroatom. H means heteroatom, and the fifth atom is also different atom. 1, 2, 3, 4, 6, 7, 8, 9. Okay, all are same, but the 10th atom and the 5th atom, the vertex are different. They're labeled as H. And the H attached to the another atom, that is 10 and 1, they are different. So that edge is defined as K. And 10 and 9 are two different vertices, so its edge is defined as K. Similarly for 4 and 5 and 5 and 6. Okay, so if I and J are weighted, then it is represented as K. If I and J are not weighted, then it is represented as 1. Okay, for example, 3, 4 not weighted, it should be 1. 2 and 3 not weighted, so therefore it should be 1. 1 and 2, it is 1. It should be represented as 1. The relation between 1 and 2, or 2 and 3, or 3 and 4. The relation between 4 and 5 should be represented as K, because they are weighted. And the vertex which are weighted are represented as H, not as 1. Otherwise 0. So these are the cases. For example, let me define the vertex at 1, 2, 3, 10. 1, 2, 3. These are the vertices. 4, 5, 6, 7, 8, 9, and 10. You can see, let me consider the first vertex 1 and 1, 0. 1 and 2 is adjacent 1. They are not weighted, that's why it is 1. Okay. And all others are, it's not adjacent, therefore it is 0. 1 and 10 are adjacent, and since the 10th atom is weighted atom, therefore its relation is defined as K, if they are weighted. Similarly, 2, it is not connected to any weighted atoms, therefore we will get only 1 and 0. You can see the fifth atom. Fifth atom, 0, 0. The first atom not connected, second atom not adjacent, 0. And the fourth atom, it is K, because that is a neighboring vertex. And the number itself, it is represented as H. If the atom is weighted, then you should not write 0. You should write H. And the next neighboring atom is K. Okay. So this is how we write to represent the weighted graphs in the matrix. Then the fourth one, that is the distance matrix. Okay, the last one in this unit, meaning that represents the shortest path, number of bonds between the atom pairs. Okay, so distance matrix represents the shortest path between the atom pairs. So it is D is equal to Dij. So Dij is equal to minimum number of edges between vertices I and J. So these are the two atoms, the vertices. The minimum number of edges between the vertices of I and J. So this represents, used to calculate Wiener index, I'll be discussing in the next recording, and describes the molecular size and shape. Let us understand this distance. Okay, this distance matrix by taking propane as an example. So propane, this is the graph. It is having 3 vertices, 1, 2, 3, and 2 edges. Okay, the distance for this is it is defined as C1, 1, 2, 3, and 1, 2, 3, 3 vertices. 1 and 1, the distance is defined as 0, and 1 and 2, this is by 1 edge, and 1 and 3, 1 and 3, 1 and 3, they are separated by 1, 2. So therefore, 2 edges. Similarly, 2 and 1, they're separated by 1 bond, and 2 and 2 is 0, and 2 and 3 is again separated by 1 bond. So therefore, it is 1. 3 and 1, 3 and 1 separated by 2 bonds. Okay, it is therefore it is 2, 1, 0. So this distance matrix captures the relative atomic separation essential for size related properties. Okay, so you can see that the distance matrix for this protein P, it is having 5 vertices, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and this is actually 3D. It is in 3D representation. You can see that 1 and 1, 0, and 1 and 2, the distance is defined as A, therefore you should write A. Okay, 1 and 3, it's defined as 1 and 3, it is defined as B, directly by the distance, not the through bonds, it is the distance B. And 1 and 4, it's 1 and 4 is defined as C, and 1 and 5 it is defined as D. So A, B, C, D. Okay, so that is how we represent the distance matrix. So if this is another example, you can just work out. So this is a distance matrix for this molecule. You can see that these are the 4 vertices labeled as A, B, C, D. A, 0, and A and B are separated by 1 and 2. So therefore, it is two bonds. And A and C are 1 plus 2 plus 1. So it will be 4. Based on the labeling, we have to represent the matrix. Similarly for B, C, D. Okay, so overall the comparison is for the 3 types of matrices: vertex adjacency, edge adjacency, weighted adjacency, and distance matrix. Where vertex adjacency represents the atom-atom bonding. It is used to understand the connectivity and Zagreb molecular descriptor. Edge adjacency matrix represents the bond-bond relation. It's used to understand the branching and also to calculate the Platt number. Weighted adjacency for bond strength or bond order or any other heteroatom to understand. It's used in advanced quantitative structure activity relationship. And distance matrix represents the bond separation. It's used in Wiener index and also the size. So overall, the molecular graphs, first we understood in the previous video molecular interactions. From that molecular graphs to matrices. And then in the next video, I'll be discussing about the numerical descriptor, and the last video will be discussing the QSAR and QSPR. That is property predictors. So this is the comparison of vertex adjacency, edge adjacency, and distance matrix for this molecule. So you guys can see all 3 are different. Okay. So since it is having 4 vertices, this will we get 4 cross 4 matrix. And edge, how many edges? 1, 2, 3, 4, 5. So since there are 5 edges, therefore it is called 5 cross 5 matrix. And distance, it is defined by 4. So therefore it is called 4, 4 matrix. You can practice. Next, this is another graph compared with all the vertex adjacency matrix, edge adjacency, distance adjacency. All of you work out, and if there is any mistake, please comment on this video. Okay, so first you should vertex adjacent matrix should identify the number of atoms, vertices. For adjacency should identify how many edges, 1, 2, 3. So there are only 3 edges, therefore we get 3 cross 3 matrix. And the distance between among 4 atoms. You can see here for the third atom, 3 and 1, it is 1 bond and 2 bonds. So and 3 and 2, 3 and 2, 1 bond and 2 bonds. Okay. So this represents how far that these two atoms separated. So this is another graph of cyclobutane with labeled as 1, 2, 3, 4 and as edges, vertices and ABCD as edges. And these are the corresponding vertex adjacency matrix and edge adjacency matrix and the distance. So all these three, using this matrix representation, the computer can predict that, okay, this molecule is having this structure. Okay, this is closed graph, dense graph. You can see that the order of the matrix, vertex adjacency and edge adjacency and the distant adjacency matrix are completely different. So this is 4 cross 4 and this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. I think this is E and this is F, I think. Okay, so totally 4 plus 2, 6 cross 6 matrix, and this is 4 cross 4. So this is another molecule for which the vertex adjacency, edge adjacency, and distance matrix are discussed. So you can see the why we are getting 3 here. For 5th atom to 6th atom, the distance. The distance between the 5th atom and 6th atom is labeled as 3. It is because 1, 2, 3. So this is the 5 and 6 are connected with 3 atoms, 3 edges. Therefore, it is called 3. Even 2 and 5 are connected by 3. 2 and 5. 1, 2, 3. 2 and 5. 1, 2, 3. So therefore, it is labeled. You can see that 1 and 5 will be 4. 1 and 5 are separated by 4 atoms, 4 edges. 1, 2, 3, 4. This represents more the number means they are far away from each other. So 1 and 5, 4 means they are far away from each other. 2 and 5, 3. So okay, that's slightly closer than 1 and 5. So that is what that computer can understand from this matrices. So with this, I'll just stop my discussion about the matrix representation from molecular interactions to molecular topology and matrix representation. In the next recording, I'll be discussing the topological indexes. Okay, so that this matrix will be represented in some numbers, numerical values. We'll understand what are the types of topological indices and what are the significance of that. Okay, so thank you. I hope you understood. We'll continue in the next third part. So this is the second part of Unit 5, and the third part will be covered in the next video. Thank you.